Okay, in this video we are going to prove a statement that follows from Euler's theorem. So the statement reads as follows: keep G is a plane graph on n vertices and m edges, okay, in which every region is a k cycle or ck, then the number of edges is equal to k times n minus 2 divided by k minus 2. So before proving this theorem, let's look at some examples to get an understanding of this particular statement. Okay, so let's start with a very simple graph. Okay, C3, a cycle on 3 vertices. Okay, and here we can see that this graph C3, it divides the plane into two regions, R1 and R2. And again we can see that this R1 is surrounded by okay, these three edges, okay, or C3. Similarly, R2, it is also surrounded by a C3. So it satisfies this condition. Every region is a 3 cycle in this case. So that says for this graph, k is equal to 3 and the number of vertices is 3. And let's find the number of edges using this equation. So that says this will be like 3 times, okay, n minus 2 is 1 and k minus 2 is 1, which is equal to 3, and here we can see that this graph has 3 edges. So okay, that equation is satisfied for this one. Okay, so let's look at another example. Okay, again we are considering a graph having, okay, k cycle regions. Okay, and this is region R1. So this R1 is surrounded by, okay, 3 edges. So suppose that we add one more vertex here and 3, okay, these edges. Okay, we can see that if you look into any region here, say R2, because this R2 is also surrounded by a C3, and similarly this R3 is also surrounded by a C3, R4 is also surrounded by a C3. Okay, so it's a plane graph anyway, and again we can see that it satisfies this condition. Okay, every region is a 3 cycle here. Okay, and so that says k is equal to 3 here and number of vertices is 4 here, and let's find the number of edges here. Number of edges will be like 3 times, okay, 4 minus 2, which is 2, divided by k minus 2 is 1, okay, that is 6, and here we can see that the number of edges in this graph is 1 2 3 4 5 6. Okay, so this graph, we do satisfy this equation. Okay, so let's look at another example where the cycles are C4 kind of thing. Okay, so let's start with this one. Okay, a C4, a cycle on 4 vertices, and again we can see that this graph C4, it divides the plane into two regions, okay, say R1 and R2. So we can say the R1 is surrounded by a cycle C4 and R2 is also surrounded by a C4, and moreover this graph is a plane graph and it satisfies this condition. Every region is a 4 cycle here. Okay, so that says 4 is k is equal to 4 and number of vertices is 1 2 3 4. Okay, and let's find the number of edges using this equation. So that says this will be equal to 4 times 2, 4 minus 2 divided by 2, okay, which is going to be equal to 4, and number of edges is 4 here. Okay, so that, okay, this graph do satisfy this equation. So let's look at one more example. Okay, again we are considering, okay, 4 cycles here. Okay, so let's start with this one. Okay, so now we have this C4 and let this be region R1. So we can say that R1 is surrounded by C4. Okay, so let's add some internal regions also here. Okay, so we can see that is R2 is another region, so it is surrounded by a 4 cycle, but here if you consider this as a region, okay, it is not surrounded by R4, not R4 C4. Okay, so we need to add some more edges here. Okay, so now we can see that this R3 is surrounded by a C4, okay, but this region is not surrounded by a C4, right? So we need to add some more edges here. So now we can see that this R4, okay, it is surrounded by a C4, but this region is not surrounded by a C4, so we need to add this edge also. Okay, so now we have these two regions. So R5 it is surrounded by a C4. Similarly, this R6 is also surrounded by C4. Okay, so now we can see that we have this graph G here, and it's a plane graph. Okay, and it satisfies this condition. Every region is a 4 cycle. Okay, it's a C4 kind of thing. Okay, so let's count the number of vertex edges here. Okay, so here k is equal to 4, and number of vertices is equal to 1 2 3 8. Okay, and number of edges will be like k times 6. K is 4, right? 4 times 8 minus 2 is 6 divided by k minus 2 is 2. Okay, so 3, which is equal to 12. Okay, so let's see whether we get the answers correct or not. 1 2 3 4 5 6 7 8 9 10 11 12. Okay, so we can see that this graph does satisfy this thing. Okay, so it worked for these 4 graphs. So let's go and prove for the general case. Okay, so if you have a plane graph in which every region is a k cycle, then the number of edges, it is going to be k times n minus 2 divided by k minus 2. Okay, so let's prove this statement. So let G be a plane graph on n vertices and m edges, okay, in which every region is a k cycle. Okay, that is every region is surrounded by a ck kind of thing. Okay, ck. Okay, so if you look at these examples, we can see that every edge lie on a boundary between exactly 2 regions. Okay, so this edge, it is on the boundary between R1 and R2. This edge is on the boundary between this R2, R3, etc. So that is true for any edge in this, in these 4 graphs. Okay, and that is true for every planar graph also. Okay, every edge, it lies on a boundary between 2 regions. Okay, in this case, that may not be true in general. For example, if you have a graph which looks something like this, in this case we can see that this edge does not lie on a boundary of this thing. Okay, but here we are said that we have a cycle kind of thing. So if that's the situation, so in general that might be okay. For this kind of graphs, we can see that each edge lie on the boundary of exactly 2 regions. Okay, so if a graph satisfies this condition, then that is true. Okay, so that says each edge. So since every region is lies on it's a k cycle kind of thing, each edge it lies on the boundary of exactly 2 regions. And that we saw from these examples, right? So anyway, this graph, it does not satisfy this condition. Okay, and let say R1, R2 up to say R sub r, small r, be the region of G. Okay, so here again we can see that if you look at a particular region R2, and if you sum the number of edges in the boundary of that region, that will be equal to 3 here, right? Okay, for R2 we have these 3 edges, so for R2 that sum will be 3, and similarly for R1 that sum will be 3, because it lies on every region is is a k cycle kind of thing. Okay, and we can see that if you add that quantity, that is the number of edges in each boundary, that is going to be equal to 2 times the number of edges, because each edge lies in the boundary of exactly 2 regions R1 and R2. Okay, so let me write down what I said. Okay, so here we have this condition. So here we can see that if you add the number of edges in the boundary of each region, so here we have R regions here, right? Okay, small r. So if you add this quantity sigma equal to 1 to n, the number of edges in the boundary of each region, the region Ri. Okay, if you sum the number of edges in the boundary of the region of in each region, we get 2 times the number of edges. Okay, so we have this condition here, each edge lies on the boundary of exactly 2 regions. Okay, so we have this equation. Okay, and here we can see that the number of edges in a particular boundary is going to be k here. Okay, because we have this condition, every region is a k cycle. Okay, so this summation is nothing but I equal to 1 to r k. The number of edges in the boundary of the region Ri is k, so that is going to be equal to 2m. Okay, so this is independent of phi, so that says we have rk equal to 2m, and from this we can find the number of regions, that is going to be equal to 2m divided by k. Okay, so we found the number of regions in that particular graph. Okay, so now we can use Euler's theorem. So by Euler's formula, we have the number of edges minus number of vertices minus number of edges plus number of regions is exactly equal to 2. Okay, so here we found this r, so that says n minus m plus 2m divided by k is equal to 2. Okay, so rearranging this we get kn. So rearranging that we get kn minus km plus 2m. Okay, kn minus km plus 2m equal to 2k. Okay, so that says if you rearrange this, you get kn minus 2k equal to km minus 2m. Okay, so we can take this out, k out here. Okay, that is equal to k minus 2 times okay, and we are solving. Okay, if we solve for m, we get k times n minus 2 divided by k minus 2. Okay, and that's what we need. Okay, so k into n minus 2 divided by k minus 2. So we proved this statement. Okay, so that says if G is a plane graph on n vertices and m edges, if G is a plane graph on n vertices and m edges in which every region is a k cycle, then the number of edges is k times n minus 2 divided by k minus 2. So it follows from this Euler's formula.